So, our speaker today is Arun Soor. His title, you can see there, is Six-functor formalism for analytic D-modules on rigid analytic varieties. So, please, Arun, go ahead.
Thank you for the invitation. Yeah, I'm pleased to speak in this seminar. Yeah, this talk will be about a six-functor formalism in rigid geometry for D-modules. So explain what that is. I should first explain what a six-functor formalism is. So is that on the next slide now? So a six-functor formalism is okay, so we start off with some category of geometric objects. I call this C, and this should kind of admit fiber products. So for instance, we could have C being schemes, like locally compact Hausdorff spaces, or in this talk, we'll focus on the case when C is rigid analytic varieties. So I'll write rig for that. So a six-functor formalism, kind of very roughly speaking, associates to each object, kind of to each geometric object, a closed symmetric monoidal infinity category. If you're not familiar with infinity categories, perhaps you can just think of that like the derived category of quasi-coherent sheaves. So I've written QX kind of suggestively for that. And you'd have the derived tensor product on that. And this association should satisfy like a very large number of functorial properties. So I'll get onto that. So originally, this idea of the yoga of the six operations was initiated by Grothendieck in his study of the functorial properties of L-adic cohomology. But in recent years, it's received a lot of attention because it's gone from being sort of a yoga to having a precise definition of what a six-functor formalism is. So this is due to work of Liu and Zheng, Gatescree and Rosenblum, Lucas Mann, and Peter Scholze in various iterations. So in this talk, we will use a definition of a six-functor formalism as formulated by Lucas Mann. Okay, so what is a six-functor formalism? When we produce six-functor formalisms, we'll also single out a collection of edges or morphisms in C, which are kind of special or shriekable. So I'll get onto that. And then this pair, CE, is supposed to satisfy some extra conditions. So for instance, edges in E have to be stable under composition and pull back by morphisms in C. And then this pair CE is called a geometric setup. So I borrowed that terminology from Lucas Mann. So what do we require? So for instance, so if I have an arbitrary morphism in C, I have to be able to associate a symmetric monoidal pullback functor, which we call F upper star. So that's like a contravariant association. So for instance, once again, continue with the example of quasi-coherent sheaves. Like if you have a morphism between affine or affine spaces, this is given by tensoring. Okay, and then to each morphism in this special class of edges, E, you associate a push forwards functor, which we can roughly think of in many examples as being like compactly supported push forwards. So, I mean, as you know, when you have the category of quasi-coherent sheaves, the push forwards functor has kind of bad properties away from the quasi-compact case. So this compactly supported push forwards is supposed to kind of bootstrap these good properties to kind of a much larger class of morphism. Then for composable F and G, these associations should be compatible with composition, right? So you should have F lower shriek, G lower shriek is FG lower shriek, and G upper shriek, so G upper star, F upper star is FG upper star. The important identities which we require these to satisfy is firstly base change. So if I do like the compactly supported push forwards and then pull back, that should be the same as doing pull back and then push forward along like this kind of Cartesian square. So for instance, G prime is the pullback of G along F, right? And F prime is the pullback of G of F along G. The second important property is the projection formula. So so F lower shriek may not be compatible with tensor products, but is required to satisfy this projection formula, which is kind of loosely says that F lower shriek behaves well with respect to tensor products. So this gets us three of the operations. So F upper star, F lower shriek, and the tensor product. So the remaining three operations for the six-functor formalism are defined to be the right adjoints of these three functors. So I guess the condition which we require is that like these three operations admit right adjoints. So the first one is just called push forwards, F lower star. The second one is called exceptional inverse image, so it's F upper shriek. And the third one is called internal HOM, the adjoint to the tensor product. So heuristically, this is what it's supposed to be. But in order to construct this, there's actually an enormous number of compatibilities which have to be checked. So the base change and projection formulas themselves have to be compatible with these composition isomorphisms, which are all data. And this leads to a potentially enormous number of things to check. So to be able to formulate what a six-functor formalism is a priori something that is highly non-trivial and difficult, which makes it remarkable that in recent years, we have been, mathematicians have been able to provide a succinct definition. So this goes via a construction which is called the category of correspondences. So, okay, so given a geometric setup, CE, we can associate it to an infinity category called core CE. So what is this category? So this category has the same objects as those of C, but the morphisms are given by spans, right? So by definition, a morphism from X to Y in the category of correspondences is given by a span. So I have to give like some other object of C, like some other scheme or topological space, which lives over X and Y with two maps to X and Y. And we're required that the arrow on the right belongs to this special collection E, where we can take shriek functors. Okay, so that's the morphism. And how do you compose those morphisms? So, so if I have one span like this, so that's a morphism from X to Y, and I have another span, so this is a morphism in the category of correspondences from Y to Z. So the way in which you compose these is you take the fiber product of U and V over Y, so that goes in the middle. So that admits maps to U and V, and then U maps X and V maps to Z. So the composition is given by this composed correspondence. So this category of correspondences is also a monoidal category with respect to a monodal structure which is inherited from the Cartesian monodal structure on C. So this is roughly an explanation of what car-CE is. And an important thing to note is that even if C is itself a one category, this construction may genuinely, or is generally speaking, an actual infinity category. So it some way necessitates the introduction of higher category theory. So what we do in a six-functor formalism is consider, well, a six-functor formalism will be a lax symmetric modal functor out of this category of correspondences, so I'll call it Q. And this lax symmetric modal functor will determine functors which we can call G upper star, which is the image under Q of this morphism from X to Y given by G on the left and the identity on the right, right? So that's morphism from X to Y. And then this gets to something which we call G upper star from QX, from QY to QX. So similarly, we have this correspondence. So X equals X and then going to Y. So that's the correspondence from X to Y. And we get this morphism, this functor, sorry, from QX to QY, right? So this is the definition of F lower Schrieg in a six-functor formalism. And I guess the fact that this is a lax monodal functor means that you also get this map from QX to cross QX to QX.
Sorry, I interrupt you.
Uh-huh.
In the category of correspondences, the map to which you apply Q in the first line, when you define G star, doesn't this go from X to Y? I mean, if my problem is as follows. The first, in the definition of G star, the thing to which you apply Q is a morphism from X to Y in the category of correspondences.
Oh yeah, sorry, you're right. This should be a morphism from X to Y. Yeah, yeah, you're correct. Yeah.
So it's QX to QY.
Yeah, that should be QX to QY. So that's a misprint.
Okay. Because the first line indicated that Q was contravariant, and the second line that it was covariant. So that's.
Oh yeah. Sorry,
this
okay. Yeah. That's that. Thank you for pointing that out. Yeah. So this should be an X, and this should be a Y.
Okay.
Yeah. Okay. So sorry about that. Okay. So So the definition of a six-functor formalism, so this is due to Liu, Zhang, Gatesbury, Rosenblum, and Lucas Mann, is that a six-functor formalism on this geometric setup, CE, is defined to be a lax symmetric monoidal functor, Q, from the category of correspondences to the category of infinity categories, such that all of these functors, so the G upper star, the F lower Schrieg, and the tensor product admit right adjoints. Why do we kind of care about this definition? So firstly, this succinct definition provides a viable way to manipulate six-functor formalisms and produce new ones out of old ones. So previously, this was something which was very difficult. It can be used to kind of streamline the proof of some quite complicated theorems. So for instance, Bogdan Zavialov showed how to simplify the proof of Poincare duality in six-functor form in the setting of a six-functor formalism in his recent paper. And sometimes six-functor formalisms can they're kind of an organizing principle. So a six-functor formalism can sometimes guide us to what the correct definitions of some objects or functors should be. So for instance, in this like Fogg-Schulze work on geometrization, they were able to kind of reinterpret ULA sheaves, which is something that is at least like notions of admissibility in terms of F-smooth objects in a six-functor formalism. So that's just an example.
Sorry, I interrupt you again. There's a
yeah.
talk. There's a question by Dev on the chat. So I read it to you. There's a purely ring theoretic correspondence by category whose objects are rings, morphisms are bimodule maps, and two homomorphisms are bimodule maps. Yeah, so morphisms are bimodules, and two homomorphisms are maps between bimodules. Is there a choice of E such that the correspondences of CE gives you this bi-category?
So given a six-functor formalism, you're talking about like, for instance, these like Fourier-Mackay kernels and things like this. Very good. So given a six-functor formalism, you can associate an infinity two category, which is called the Luzang category, in which like the space of morphisms from X to Y is given by like Q of X times Y, as far as I remember. So and the morphisms are given by kernels, but that's not the same as the category quasi E itself, right? So a six-functor formalism gives you a way of to construct this this category. So this is, yes, you can read about this in, for instance, Peter Scholz's notes. Okay, hopefully that answered the question.
Okay.
Okay, so the setting of this work is in rigid analytic geometry. So rigid analytic geometry was introduced by Tate, and in many ways it behaves very similarly to complex analytic geometry. So complex analytic geometry, or the theory of holomorphic functions, is very rigid as well. So perhaps that's where the name comes from. But rigid analytic geometry is done relative to p-adic fields, which is by definition a complete extension of QP in my case, rather than the complex numbers. So in this talk, we're going to consider separated rigid analytic varieties. So that's what the S means here. And with steady morphisms. So I'll tell you what a steady morphism is later. And then the aim of this talk is to describe how to produce a six-functor formalism from, on rigid analytic varieties. So like, as in our previous definition, that would be a lax symmetric nodal functor from correspondences on rigid varieties with some class of morphisms to the category of infinity categories. And this class of morphisms, this like special class of morphisms, we're going to construct it so it has kind of good stability properties. So this particular six-functor formalism, so like the value of like Chris on an object or on a rigid variety is going to be similar to modules over the sheaf D cap of infinite order differential operators, which is being considered by Ardakov and Wadsley, or rather introduced by them.
Will divided powers be involved?
There's no divided powers. It's because this is like characteristic zero. So
because we are over QP, yeah.
So we're over QP. So there's no like crystalline differential operators or anything like that. So this work is quite similar. We're kind of similar in spirit to work of Rodriguez Camargo, and it's inspired by work of Andy Jiang. Okay. So I'm afraid, yeah, this slide is slightly technical. But in order to first construct a theory of D modules, we have to have it in this way. We have to have a theory of quasi-coherent sheaves on analytic varieties. So now I'll explain how to construct a theory of quasi-coherent sheaves on analytic varieties. So firstly, we start off with an affine rigid space. So an affine rigid space, like affine rigid spaces, we can just think of as the opposite category to affine algebras. And affine algebra is a K-Banach algebra. So Banach spaces, they embed into the category of bornological spaces. So we can think of bornological spaces as being some kind of generalization or alternative to locally convex vector spaces, but with kind of better homological and algebraic properties. Okay, so we view A as a monoid in the closed symmetric modal category of complete bornological K vector spaces. So that's what C-born K means. This is step one. So then, given this Banach algebra, we can consider mod A. So that is the quasi-abelian category of modules over the monoid in C-born and K. And then Jack Kelly, in his work, has defined model structures on the category of unbounded chain complexes valued in an elementary quasi-abelian category. So elementary you can think of as being some kind of like something that is similar to being Grothendieck abelian. So now when you have a model category, you can consider the infinity category, which you obtain by firstly taking the nerve of the one category and then inverting the weak equivalences. So that is called, like this procedure is called passing to the underlying infinity category of your model category. And this gives us our definition of QCO on an affinoid rigid space, right? So QCO of an affinoid rigid space is defined to be, is QCO compactly generated? It is compactly generated by objects of the form A tensor C naught S, where S is some set. So C naught is like your non-Archimedean like counterpart of an L1 space. Okay, so for each morphism of affine rigid spaces, you can consider the derived pullback. So that is just given by the derived tensor product. So that gives you a functor from QCO of SPA. Oh, I've got that the wrong way. Sorry, this should be A tensor over B. So, okay, so you can consider the derived pullback, and this will get you a pre-stack on finoid rigid spaces. And I've written this notation here. So we can think, so this notation means, so these categories are, they're compactly generated, in particular presentable. So the L means all the functors are left adjoints, right? So all these pullback functors are left adjoints. So stable means that the categories are stable, infinity categories. And then com just means that like they are symmetric monoidal categories, right? So we have a pre-stack of presentable, stable, symmetric monoidal infinity categories with left adjoint functors between them. So that's all this means. So this is a very good situation to be in. We have lots of nice categorical properties. Okay, so what is the point of this? Is that so this pre-stack QCO, so a priori it's just a pre-stack, but the category of affine algebras has a Grothendieck topology on it, which is called the weak G topology. And this pre-stack satisfies descent with respect to this weak G topology. So in other words, it's a sheaf in the weak G topology. So this is kind of corrects the properties of the naive definition of quasi-coherent sheaves. I guess like the, yeah, I guess if you take chain complexes instead of just like modules, then you can get a well-behaved theory of quasi-coherent sheaves on analytic spaces. And then now you have a sheaf in the weak G topology. The weak G topology is a basis for the strong G topology on all rigid spaces. So it's like a theorem that if you can't extend this functor QCO along the map from affine rigid spaces to rigid spaces with the strong G topology, it makes it into a sheaf in the strong G topology. Okay, so we need at least some to establish some properties in order to get a six-functor formalism. So for every map of rigid spaces, because QCO is now like a pre-stack in the strong on rigid spaces, you have a pullback functor, and this pullback functor admits a right adjoint. So this is kind of formal just because it's co-limit preserving and we work with presentable categories. And then is the weak G topology equivalent to the homotopy Zariski topology? I mean, it's definitely it is definitely coarser than the weak G topology. I think there might be some result of like Kremnitzer, Ben-Besat, which says that the weak G topology is equivalent to the homotopy Zariski. I think is equivalent to the homotopy Zariski topology. I think. So you can read it in that paper from 2017. I can't remember the title off the top of my head. So if F is quasi-compact, then F lower star is co-limit preserving. So the example you should have in your head is just F is a map between affine and rigid spaces, and then F lower star is just the forgetful functor at the level of modules, so therefore it preserves co-limits. It commutes with restriction to admissible opens, and it also satisfies this projection formula if F is quasi-compact, right? So there's a few kind of basic properties which we have to establish. So if we want to get a six-functor formalism, a necessary condition is to have base change isomorphisms. So it's kind of a well-known fact, even in algebraic geometry, that for arbitrary morphisms, you don't have base change if you have you don't have base change for quasi-coherent sheaves. If you work with chain complexes, and the basic reason for this is because many maps are not flat, for instance. So the kind of well-known fix to get base change to work would be to use some kind of derived geometry or enhance the category of rigid spaces to some kind of category of derived rigid spaces. However, we will not adopt this approach. We will actually adopt a different approach, which is to restrict the class of morphisms to kind of exclude the bad ones where base change doesn't hold. So we'll work with steady morphisms instead. Okay, so let me explain what a steady morphism is. So a steady morphism, this is a notion that was borrowed from Lucas Mann. So a morphism of affinoid rigid spaces is called steady if for all, I've got these the wrong way around. So this should say F from SPB to SPA, and this should say G from SPC to SPA. Okay, sorry.
It would be easier if you stuck to homomorphisms of algebras.
Yeah, it would be maybe just erase SP here. Yeah, that would also fix it. Okay, so a morphism of affinoid like algebras is called steady if for all morphisms of affinoid algebras, the natural morphism from the derived tensor product to the tensor product is an isomorphism. Okay, so it was asking for like some vanishing of Tor groups. And a morphism of rigid spaces, so a rigid space is locally modeled on affine spaces, is called steady if it's steady locally on the source and target. Okay, so okay, so in order for this to be a useful notion, we have to provide some examples of steady morphisms. So the inclusion of an admissible open subset is always steady. So this is a correlate of the work of Bembasat and Kremnitzer. And also the structure morphism of any rigid space is always steady. So steady morphisms also have good stability properties. So they're stable under composition, they are stable under base change, and they have like kind of this kind of 2/3 of the 2 out of 3 property. But the reason why they're important is because they satisfy base change, right? So if G is steady, then for any quasi-compact morphism F, you have a base change isomorphism. So this is kind of the last thing that we need to establish in order to get some kind of six-functor formalism. Okay, so this is what a steady morphism is. And if we restrict to the class of steady morphisms, then we can apply the results of Lucas Mann and obtain a six-functor formalism for rigid spaces, separated rigid spaces, but with where we restrict the class of morphisms to steady morphisms. And then the class E that we take initially is just quasi-compact morphisms. So we obtain this quasi-coherent six-functor formalism. And then by a kind of formal procedure, so if you look at the appendix to Lucas Mann's thesis, he tells you there's various ways you can do count extension to extend a six-functor formalism, the class E of morphisms. So by this kind of formal procedure, which is articulated in theorem 4.20 of Peter Scholz's six-functor formalism notes, you can lift this to a six-functor formalism on like rigid spaces with a much larger class of morphisms E. And this class of morphisms E has good stability properties. So it's kind of local on the source and target in a precise way. So if you're interested in like the details of this, you can see Peter Scholz's notes on six-functor formalisms. Okay, so one thing that will be an important ingredient or an important and useful operation as well to do on quasi-coherent sheaves is local cohomology. So these ideas were inspired by work of Andy Jiang, and there's also a kind of classical theory of local cohomology for rigid spaces, which was developed by Mark Kissin. So yeah, let me tell you what this is. So we're just going to consider a subset of a rigid space with the property that its complement is an admissible open, right? So S is not necessarily an admissible subset itself. It could be like a Zariski closed subset or closed analytic subset. And then we look at its complement, which is an admissible open, right? So the canonical example would be S is a Zariski closed subset. And then let's let J be the inclusion of the complement. We're going to impose this hypothesis that the upper Schrieg-functor, so that like this exceptional pullback along J is the same as the usual pullback. Okay. So we impose this technical hypothesis. So now we can consider the category of pairs where the objects is a rigid variety and then one of these kind of special subsets. And the morphisms from two pairs is a morphism F from X to Y, such that F of S is contained in T, right?
You missed the T.
Sorry, Y
It's YT. Yeah.
So YT. Sorry, that's another typo. So a morphism f from xs to y comma t is a morphism f from x to y such that f of s is contained in t. What should the value of qco be on one of these pairs? We define the value to be, so I write it like this, gamma s qco x. So it's like the sheaves with, the objects with support along s. So by definition, that means it's the full subcategory of objects, which become like 0 upon pullback to the complement. So that's the meaning of this category. Okay, so this tautological inclusion of sheaves that are supported along the subset, it has actually both, in this setting, both a left and a right adjoint. Okay, so the right adjoint to this inclusion of sheaves with support is what we call the local cohomology functor. And the left adjoint, I guess I didn't really know what this functor is called, so I just call it I inverse S. So this is what what we call inverse image. Okay, so with the aid of these additional operations, we can lift QCO to a six-functor formalism on the category of, I guess, in this case, I just restricted to quasi-compact and separated pairs. So that means X is quasi-compact separated. And together with steady morphisms. So we obtain a six-functor formalism in this way. So by setting QCO XS is the sheaves with support along S. And for example, if you have a morphism from XS to YT, the upper star pullback along this morphism is like, first I do the usual upper star pullback, and then I do the inverse image along S. Also like sorry, this did not have a -1. The upper Schrieg functor is, first I do the upper Schrieg pullback and then apply the local cohomology functor. Okay. So this category of pairs is useful, but there's some kind of redundancy because the category QCO XS of like quasi-coherent sheaves with support along S does not depend on the whole ambient space X, right? So it only really depends on a kind of open neighborhood of S. So this notion we can formalize using the category of germs. So this is a notion that was introduced by Berkovich in his paper about étale cohomology. So we'll just borrow this into our setting. So the category of germs is a localization of the category of pairs. So we have to define which system of morphisms we localize with respect to. So I'll say a morphism phi belongs to this system, capital Phi, if it induces an isomorphism of X with a neighborhood, an open neighborhood of T and Y. Okay. And then this system actually admits a calculus of right fractions. So we can describe the localization to the category of germs fairly well. And the category of germs is defined to be the localization of the category of pairs at this class phi. And I'll write XS goes to square brackets XS for the image of XS under this localization functor. So this six-functor formalism, because like the category QCO XS doesn't really depend, or I mean, it's essentially kind of descent result, which says that the six-functor formalism for the category of pairs induces one for the category of germs. Okay. So that's the six-functor formalism for the category of germs, and this will be our basis for what follows. Okay, so our category of stacks, which we're going to consider, we're going to consider quasi-coherent sheaves on stacks because like this is one way we can think about D modules, is the category of pre-sheaves on germs, but valued in infinity groupoids. So that's going to be our category of stacks. And we can, I mean, by count extension, we can lift the six-functor formalism from the category of germs to the category of pre-sheaves on germs. I mean, we just think of pre-sheaves really as being like the free co-completion of the category of germs. So this is really all we do is like all this really is somehow like the unique co-limit preserving extension of QCO. And then we can again obtain a good collection of morphisms E tilde with good stability properties by this kind of formal procedure, which is used to Peter Scholze. So now we have this six-functor formalism, and this is what we're going to use to directly construct our six-functor formalism for D modules. So I guess the advantage of working with pre-sheaves is it corrects the defect of like our category of geometric objects, which is that you can't take kind of random co-limits of geometric objects, right? So now we can take co-limits of our kind of spaces, and in particular we can define quotient objects. So that is the utility of using pre-sheaves. Okay.
Sorry, there is another question by the in the chat about the descent condition.
Oh, so there's no G topology on this category. I guess we could just call this the category of pre-stacks. But yeah, I don't require my stacks to satisfy any kind of descent condition or yeah, so they are just pre-stacks. Like I don't do any kind of sheavification. Okay. So for a rigid space X and any kind of integer n greater than or equal to 0, you can consider this germ, which is so x like x cross x cross x m plus 1 times. And then there's an obvious kind of closed subset of this, which is just given by the diagonal. So we obtain this germ like x m plus 1 with the diagonal, right? And then like if I let n vary, I can arrange these into a simplicial object, right? So like at the beginning, I just have x with x. Then the first thing will be x cross x with the diagonal. This has like 2 projection maps and 1 degeneracy, and so on. So if you go all the way along, you obtain this simplicial object. And then our de Rham stack is just defined to be the co-limit of this simplicial diagram, right? So because we're working in pre-sheaves, we can just take that co-limit because this is like the free co-completion.
So let me ask something. So say you have a ring, an algebra, right? And then you take you can form a co-simplicial object where in the nth term you have the n plus 1 fold tensor product.
Yeah.
And then there's the diagonal ideal there, and you can form a pro object by dividing by the powers of this.
Yeah.
And this the thing that you get computes infinitesimal cohomology of the RAM, if you want. So
Yeah,
is this in analogy to? So is
it,
that
it
the
is an
idea of this the RAM?
yeah, it is analogous. So I'll answer your question. So you can consider the affinoid algebras, which is like A tensor A tensor A tensor A, if X is SP of A, right? So you can consider the system of open neighborhoods, which contains the diagonal, right? And the system of corresponding localizations of A tensor A. Then you can take the co-limit over this system. So now what you get is an end object, or like a bornological space, which is the co-limit of like A tends to A localized at U, where U runs over the neighborhoods of the diagonal.
So
And
it's
now,
like the tube construction.
yeah, it's like the tube around the diagonal. So it's if you've seen Alexander cohomology or Čech-Alexander cochains, it's quite similar to this. And then there's a relation between Čech-Alexander cochains and infinitesimal and de Rham cohomology and things like this. Yeah. Okay.
Okay. Thank you.
Uh,
So just to be
uh-huh.
fastidious, the
Yeah.
delta should also have some index, right? Because it varies with the
Yeah.
n.
So yeah. So the delta should be like the end. I didn't want to, yeah. So the delta should be like the embedding of the diagonal x n plus 1 times uh in x n plus 1. Is there a relation between rigid cohomology? I'll answer that question. I'm not sure about the answer to that question, but I'll perhaps answer that at the end. Okay, right. So this functor x goes to x to Rom ends up preserving fiber products. So this kind of fiber product preserving functor induces a functor between the respective category of correspondences. So I get a function like this, which just sends the object x to the object x to Rom. And then I can compose this with the six-functor formalism that I had and obtain the six-functor formalism like Chris, whatever, to cat infinity. So this approach of directly constructing the six-functor formalism, like in the algebraic setting, like Peter Scholze discusses this in his six-functor formalism notes. And like you can read about this, or it's a sort of similar in spirit to what like Rodriguez Camargo does. Okay, so by definition, we have Chris X is Qco X to Rom. So that's just how we constructed it. But we want to understand this category better. So there's a canonical morphism. So I've kind of omitted notation here. So by X, I mean the germ like X comma X. And then there's a morphism in like the category. So like germs embeds fully faithfully into pre-sheaves on germs. And then like you have a map, which is just like the zeroth thing, like the inclusion of like the zeroth thing into the co-limit or whatever, right? So I've simplified notation here, but there's a canonical morphism, P from X to X of Rom, which you think of as a covering. And in this situation, this actually satisfies P lowest streak is P lowest star. So you get an adjoint triple, right? So P upper star is left adjoint to P lower star, which is left adjoint to P upper shriek. So I can consider these three functors, like the corresponding push and pull from Q of X and Q of X to Rom. So I can push back, I can push forward, I can do upper shriek pull back, I can do upper star pull back. So we can try and understand Q co X by the monads or comonads of these adjunctions. So the theorem is, and this is more or less a theorem about descent. So as you may be aware, descent and monadicity are sort of two sides of this, or descent and comonadicity are sort of two sides of the same coin. So the adjunction between upper and lower star functors is comonadic, and the adjunction between lower star and upper shriek is monadic. So that allows us to describe QCO of X to ROM as a category of modules over the comonad P upper star, P lower star, or the monad P upper shriek, P lower star. Okay. Okay. So we've now changed the question of trying to understand QCO X to ROM into a question of understanding this monad and this comonad. So how do we understand this monad and comonad? So there's actually a Cartesian square. So this follows by some kind of formal stuff because we started off with a groupoid object. So we have a Cartesian square where these two maps are both P, and these are both X, and then this is X cross X with the diagonal, right? This So base change tells us that if I do P upper shriek, P lower star, that is the same as doing like push pull the other way around, right? And if you remember like what our push pull functors were for the category of germs, then that is the same as doing like upper shriek along pi 2, then you take local cohomology along the diagonal, and then you push forward along pi 1, right? Or you can, I've written the 1 and 2 the other way around here for technical reasons. But so for instance, if I do lower star push forward and then upper star pull back, that's the same as doing push pull the other way around, but now with the upper star functor. So you have to obtain these base changed isomorphisms. And it turns out that this obtains the structure of a monad from this isomorphism. And this endofunctor is precisely differential operators. So if you think of the definition of Grothendieck differential operators, like for instance in algebraic geometry, this gives you back the same, but we're now taking some kind of analytic local cohomology along the diagonal. And then this other comonad, so this obtains the structure of a comonad through this isomorphism. And this is called the comonad of jets. So I guess we can describe QCO of X to ROM as modules over the monad of differential operators or co-modules over the comonad of jets. So the relation between this monad, so this monad D infinity, which I introduced on the previous slide, is so for instance, when X is a smooth affinoid with free tangent bundle, we can look at the action of this monad on the unit object. So just the tensor unit in QCO X. So I've written that as 1x. And then we can look at the action of this endofunctor on this unit object. And it turns out that in that setting, it gives you back this thing d cap x, which is these infinite order differential operators, which were considered by Ardakov and Wadsley. So QCOX, you remember, if X is affinoid, it's just like chain complexes. So we just view that as an object concentrated in degree 0.
Sorry, I'm not familiar with the work of Ardakov and Wadsley, but is the requirement that the tangent bundle be free related to the fact that they only consider that case, or that you cannot do it when it's merely projective?
So it should be possible to generalize this to smooth rigid space by gluing. But like I mean, this is the case in which I did this calculation. So I mean, when you have a free tangent bundle, it's just much easier to write down formulas and things like this. Like étale coordinates and so on. And then the last thing I'll say is that, okay, so this looks like some kind of complicated looking formulas, but using this description of Chris X as like modules over the monad or co-modules over the comonad, we can actually use this to give some kind of somewhat explicit formulas for the 6 operations. So the F deram upper star is just well, it like the meaning of this is that F upper star of something in QCoX, or the F upper star of something in here naturally carries the structure of something in here. So at the level of like after applying the forgetful functor, like it is just the same as F upper star of quasi-coherent things. The F deram lower star is given by this kind of more complicated formula. So it ends up being more convenient to like use like one description of the category as the like the input, and the other description of this category as the target. So similarly, we can give a description for F deram lower shriek. So as a functor from like the modulus over D infinity to co-modulus over J infinity. So F upper shriek, like if I mean the level of Q co X as a functor from modulus over D infinity to modulus over D infinity is just given by the upper shriek pullback. And then the tensor product is the tensor product, if we view these things as modulus over J infinity, is just inherited from the tensor product on Q co X. And then we can also give a formula for the internal hom. So yeah, so that's the last thing I wanted to say. And here's some references.
Okay, thank you very much. Are there any questions from the participants? I see Deb has deserted us. So
Oh yeah. So it seems like Dev has a question. Oh, so the relation
okay.
RAM stack and rigid cohomology. So I think I've done everything. So I've done everything in terms of rigid varieties here, and I think there is I mean, okay. So the relation between rigid cohomology. So as you know, when you have D modules, the push forward, like the D module push forward from X to a point. So if I take this structure sheaf and take the D module push forward from X to a point of the structure sheaf, that gives you back de Rham cohomology in the classical setting for like complex analysis or algebraic geometry. So in this setting, I expect this. So you can show that the push. So if I have an affinoid rigid space, and I do the F de Rham lower star along the map F from X to point, then you can calculate this in terms of these Čech-Alexander cochains, and then expect when X is smooth, these Čech-Alexander cochains to compute de Rham cohomology, like the kind of naive de Rham cohomology of the rigid space. But as you know, the naive de Rham cohomology is very pathological for rigid spaces. Like it fails to be exact in there's no Poincare lemma for rigid spaces. So for this reason, the relation between like kind of this and some kind of de Rham or rigid cohomology is not so clear. But it is possible that if we replace, I mean, all of this stuff we could do in the same way, perhaps for dagger varieties instead of rigid varieties. In that setting, there's a better behaved theory of de Rham cohomology. So perhaps that would work. I'm not sure.
Sometimes, I mean, when you take, I've seen the dagger completion viewed as a kind of a smooth subalgebra of the rigid thing. So like you take an affinoid and then say you take the polynomials in n variables, the affinoid version, so you periodically complete and tensor with QP, say. and then you can view the dagger as a sub object of that. So I understand that this is functorial, so that you could, without leaving the realm of rigid varieties, talk about the rigid cohomology of them, right? So like the dagger complex, the RAM complex, which is the good one. I think it might be functorial on rigid spaces.
Yeah.
But maybe I'm very wrong, because I mean, if you see in some papers, they write, so they write, say K, then lang, this less than sign, and then x1, xn, and then the more than sign. This is the periodic completion, right?
Yeah.
And then they put the dagger on top of that. As if the dagger were a functor of this. Like sticking to some subalgebra. I mean, of all the series, you take those that have a polynomial growth or something, or linear growth. Maybe this is a functor of the rigid spaces themselves. I don't know.
Yeah, I'm not so familiar with these things about because there's definitely a completion functor from that's like a faithful functor from dagger spaces to rigid spaces. So and then like I guess the question is some kind of
whether you can go back.
Whether you can go back, and then whether the de Rham cohomology, the good one, is independent of this. I mean, it might be related to like Monsky and Washnitzer way back to their work.
Yeah, there's a question by Dev on localizing invariants.
Okay, so this question about localizing invariants. So in this case, QCO is compactly generated, but it is not a dualizable category. The reason for this is because it is not compactly generated by dualizable objects. The compact generators of QCO are like C0S or L1 spaces, and these are not dualizable in the analytic setting, right? So we're not in a setting where we have a dualizable category. So if you wanted to attach localizing invariants, you have to work with dualizable categories. So for instance, like Sasha Efimov recently uploaded his paper about K-theory of like large categories. So we still need our categories to be dualizable. There is a way to do this in analytic geometry, it seems, by using these so-called nuclear sheaves, which I've not looked into in this work. But these like are these are they should be something like RLF1 co-filtered limits. So RLF1 filtered co-limits of like dual nuclear Frechet spaces or something like this. Or like dual nuclear Frechet A modules. So you can consider things like this, and you get a dualizable category. And then this is the sort of thing which you can possibly attach localizing invariants to. So I guess so one reference for that would be in the condensed math setting, would be the thesis of Gregory Andreichev. And another one would be Sasha Efimov's recent paper. But yeah, it would be interesting to do this in some kind of Banach or bornological setting. Like the same definitions should exist. I remember Jack Kelly said that he thought about this.
Yeah. Yeah, Dev says they working with Jack on that.
Uh-huh. He's wondering what happens in the setting of D modules. Yeah, I'm not sure if I'm not sure about I'm not sure if working with D modules would somehow get around this thing about the category not being dualizable. I don't know actually.
I mean, some very stupid elementary thing. When you do normal the RAM cohomology in the algebraic geometry setting, in the smooth case, you can view the RAM cohomology as some, I don't recall if it's an X or a Tor on the ring of differential operators. So do you expect that with the right, perhaps daggerized version of the RAM of the differential operators, that you could get rigid cohomology described in such a way?
So I think perhaps if you like somehow systematically use dagger space in this work, then it possibly would be the case that if you take if you map F from X to Y and you take the push forward along F, like the de Rham push forward or like the F de Rham lower star in this setting of the structure sheaf, then this will give you relative de Rham cohomology. Yeah, I mean, it's nice because for instance, like the fact that this is D module push forward, like it tells you that like the push forward thing also has a connection. So like you get like Gauss-Manin connection as well out of this.
So Dev, do you have any further questions? Okay. So I think we're done here. Thank you very much for a very nice talk. And we'll stop the recording now.